let U be a non-empty open and convex subset of some Euclidean space, and F on U to R a function. Assume that F is differentiable on U. Now, F is concave if and only if the derivative of F is non-increasing on U. F is convex if and only if the derivative of F is non-decreasing on U. F is strictly concave if and only if the derivative of F is decreasing on U. And finally, F is strictly convex if and only if the derivative of F is increasing on U. Again, we will prove the concave version because the rest is similar. So this is a biconditional. First, let us prove the only if part. That is, let us assume that F is concave and then prove that its derivative is non-increasing on U. So first, assume that F is concave. Well, to show that the derivative is non-increasing on U, we need to show that dfx minus dfy evaluated at x minus y is less than or equal to 0. So let's start by taking any xy in U. Take any xy in U. But we know from the preceding theorem what the derivative of f at x and the derivative at U are base. Now, by the preceding theorem, we have dfx at y minus x is larger than or equal to f of y minus f of x, and dfy at x minus y is larger than or equal to f of x minus f of y. What we need is df of x at x minus y minus df of y at x minus y, that's actually less than or equal to 0. So, if I have dfx at x minus y, so this is minus 1 times this. So, well, I'll have minus 1 here. This is larger than or equal to f of y minus f of x. But if I multiply both sides by minus 1, well, let me write it once more. Thus, df of x, well, this is, df of x, x minus y, that's less than or equal to f of x minus f of y. Now from here, also, I need minus the f of y, this minus the f of y at x minus y. This will be less than or equal to f of y minus f of x. Now if I add these side by side, this implies that df of x minus df of y, now they're both at x minus y, that is less than or equal to the sum of these, but that's 0. So the derivative of f is non-increasing on u. So that takes care of the only if part. Now let's consider the if part. Let's assume that the derivative of f is non-increasing on u. That should imply concavity. Conversely, assume that the derivative of f is non-increasing on u. Well, to show concavity, we will actually take x and y and show that f of tx plus 1 minus ty, that's larger than or equal to tf of x plus 1 minus tf of y. So let us take x and y in u, but let us just confine ourselves on what happens on this line segment. What will be the advantage of this? Well, this will actually reduce the problem to one dimension. We will first translate the problem to this smaller one-dimensional world. We will utilize this hypothesis over here, and then what we get, we will translate back to the larger dimensional world. So we'll take advantage of what we know in the one-dimensional world about concavity of functions. That is about concavity of a function which is real valued and is of one real variable. So let xy be in u. Now, what will be done below, that will also be valid in a trivial case for x equals y, but I have to, what I can take x different than y, because for x equals y, the concavity condition that always holds. F of tx plus 1 minus tx, that's f of x, and the right-hand side, that's f of x as well. With x different than y. Now I can trace all the points between here by forming lambda x plus 1 minus lambda y when lambda is in the unit interval 0, 1. So let me define that as a function. Now define g on 0, 1 into u by g of lambda equal to lambda x plus 1 minus lambda y for each lambda in 0, 1. Moreover, let phi be the composition of f with g. Now this will be on 0, 1 into r. This phi will be a real valued function of a real variable. Now what we'll do is we will show that this phi is concave, and then using the concavity of phi, we will get the concavity of f. So translating the problem into a one-dimensional case, that will be achieved via this phi function. Right? Now, is this function of lambda, it's a function of a real variable, is it differentiable at each lambda in the open interval from 0 to 1? Yes, and well, it actually is. Well, let me first write that. Now take lambda in 0, 1. Now, well, this is clearly g is differentiable at lambda, and is f differentiable at g of lambda? Well, g of lambda, that will belong to u, and we know that f is differentiable on u. And f is differentiable at g of lambda. So we can use the chain rule here in forming the derivative of this composite function. Now, we wish to compute what phi prime lambda is. Now this is the calculus derivative. But we know that this is the linear map which represents the calculus derivative evaluated at 1. Well, for this, the linear map which represents this is, which takes each u to phi prime of lambda times u. But when u is 1, the image of 1 under this, that's just phi prime lambda. But this is equal to d f circle g of lambda evaluated at 1. So this is just a linear map as a whole. This is the value of that linear map at 1. Now, by the chain rule, this is the composition of two linear maps. One, the derivative of f at g lambda, and the second, the derivative of g at lambda. So this is the derivative of f at g lambda, which is just lambda x plus 1 minus lambda y, a point here. This composed with the derivative of g at lambda, and the whole thing evaluated at 1. Now, by definition of composition, this is df g lambda, this linear map applied to dg lambda at 1. But what's dg lambda at 1? Well, actually dg lambda at 1, now that will just be, it's the derivative of this with the real variable lambda. These are vectors, but that will be just x minus y. So this is just df at g lambda evaluated at x minus y. This is equal to x minus y. Okay, now let's keep this. Now what we wish to show is that this phi prime is non-increasing on the interval 0, 1, on the domain of definition of phi. It's 0, 1. If it's non-increasing, if this derivative, which exists, if it's non-increasing on here, then this will mean that phi is concave as a real valued function of a real variable. Then we will translate that to concavity of the function f we started with. But for that, we have not made use of this derivative being non-increasing on u. Okay, now take lambda 1, lambda 2 in 0, 1 with, say, lambda 1 larger than lambda 2. We will show that phi prime lambda 1 is less than or equal to phi prime lambda 2. But in doing so, we have to use that the derivative of f is non-increasing on u. So let's consider the points on this line segment which correspond to lambda 1 and lambda 2 respectively. So u1, that will be g of lambda 1, and u2, that will be g of lambda 2. Now, since the derivative of f is non-increasing on u by hypothesis, what shall we have? We will have df u1 minus df u2. This evaluated at u1 minus u2, this will be less than or equal to 0. This is just by definition of the derivative non-increasing. U1 and U2 are points on this line segment, thus they're points in cap U. Now, what's U1 minus U2? Now, U1 minus U2, this is G of lambda 1 minus G of lambda 2, but that's lambda 1x plus 1 minus lambda 1y minus lambda 2x minus 1 minus lambda 2y by definition of G. So you have 2 points on here. One corresponds to lambda 1 minus lambda 1 to this and this. But this is equal to x lambda 1 minus lambda 2 times x. Then here, this is 1 minus lambda 1. This is minus 1 minus lambda 1. So plus lambda 2 minus lambda 1 y. But that's equal to lambda 1 minus lambda 2 times x minus y. Now, then we have this. So, by linearity of both of these, thus they're both linear. So, well, this is what we have here in the argument. But then, by linearity, we can take the scalar lambda 1 minus lambda 2 outside the scope of differentiation. So, well, let me write it. Lambda 1 minus lambda 2 times df u1 minus df u2 of, well, what remains is x minus y. This will be less than or equal to 0. I have just written this here for u1 minus u2 and utilized that this difference function is linear since both ingredients are linear. But this is positive. Lambda 1 was assumed to be larger than lambda 2. Well, I can divide by this, and I get this. Well, so we have dfu1 at x minus y less than or equal to dfu2 x minus y. That is df, what was u1? That was g lambda 1 at x minus y. That is less than df g lambda 2 x minus y. But do we know what this is equal to? Well, df g lambda at x minus y, that was phi prime lambda. So this is phi prime lambda 1, and this is phi prime lambda 2. So phi prime lambda 1, that's less than or equal to phi prime lambda 2. But what does that mean? Lambda 1 was larger than lambda 2. Well, having this, thus phi prime is non-increasing on 0, 1. But from one-dimensional calculus, we know that that means phi is concave. So, phi is concave. Now, the next question is, how can we use the concavity of phi to obtain the concavity of f? Well, the concavity of f, well, it's f of lambda x plus 1 minus lambda y. That should be larger than or equal to lambda f of x plus 1 minus lambda f of y. But when do we get f of x here? For what value of lambda? If I take lambda equal to 1, well, then 1 minus lambda is 0. Then g of 1, that will be x. G of 0, this g of 0, that will be y. Okay? So, now for any lambda in 0, 1, f of lambda x plus 1 minus lambda y. This is simply phi of lambda. This is g of lambda. So this is f of g of lambda, but we refer to that as phi. And I'm interested, if I'm to get f of x and f of y, what happens to this function at 0 and 1? Lambda equals 0, that corresponds to y, and lambda equals 1, that corresponds to x. So I can write this then, phi lambda times 1 plus 1 minus lambda times 0. I can write lambda as a convex combination 1 and 0. But since phi is concave, this will be larger than lambda times phi 1 plus 1 minus lambda times phi of 0, since phi is concave. But this is lambda f of x plus 1 minus lambda f of y. Thus, f of lambda x plus 1 minus lambda y is larger than or equal to this. Well, we kept x and y fixed, but they were arbitrary. If x is equal to y, this holds anyway. So, f is concave. Rest similar and is left as an exercise. Okay? Any questions to this? I advise you to go through the steps again, but the idea is to translate this to a one-dimensional problem, solve it there, but in getting that this one-dimensional function, that is a real-valued function of a real variable, that has a non-increasing derivative, we use that the derivative of f itself was non-increasing. Now we have shown that phi is concave and then translated that back to the concavity of f. So that takes us to our fifth. That's the fourth characterization of concavity and the like. Well, what was the last characterization in the one-dimensional case we mentioned, well, if f is a real valued function of a real variable, and if it's twice differentiable, then f double prime, that being less than or equal to 0, which corresponds to the derivative f prime being non-increasing, that was equivalent to concavity. F double prime being larger than or equal to 0, that corresponds to convexity. Okay? Now for the strict versions, there we have a problem. These are one-sided actually. Now why is that so? Take for example, this. Is this concave? Yes. Well, assume this is f of x equal to minus x to the fourth. Okay? It will have something like this. Its first derivative, f prime x, that will be minus 4x cubed, and f double prime x, that will be minus 12x squared. Is this strictly concave? Yes, this is strictly concave, but this will become 0. The second derivative, everywhere else, it's less than 0, but at this point it becomes 0. For the strict version, the equivalence is not exactly there. It breaks down, it's one-sided, but for the non-strict versions, we'll have equivalence. But in order to have the counterpart of this, f double prime less than or equal to 0 or larger than or equal to 0, we need to introduce, in the generalized case, in the generalized context, the second order derivative. Now, the first order derivative, we can refer to that as a linear form. The second order derivative, that will be related to what one refers to as a quadratic form. Well, in fact, the nth derivative, that will be associated with what one calls an n-ary form. Okay? So we need, for that, well, I guess you have information about quadratic forms, but I will review that, okay? But the well-known theorems, well, I will not prove them because that's from linear algebra. Well, you can check the proofs, and that's not, the proofs of those theorems will not be part of the course anyway. So, any questions so far?